This screenshot here is taken from the plugin called Octopus, and you can see, if you think about Galapagos and how it lists all the iterations and gives it a value, this is what Octopus looks like. So with Octopus, think of it as if I have 3 sliders, right? So X, Y, and Z, these represent the 3 dimensions. And then it plots 3-dimensionally every single iteration or geometry in that 3D space based on the input sliders that I've given it, yeah? So let's say if I've given it a 1, it'll be here. If I get a 0.1, it'll be up here, and then a 1 here. So it'll be one of these here, this one here, for example, yeah, small. And then the color is based on, the green means it did well, red means it didn't do well based on the fitness criteria, yeah? So this is what Giuseppe is saying. So it's visualizing, and if you read your brief, in the brief it talks about exploring the opportunities of the design space, and this is what the the concept of design space is. It's kind of the different variations and options you have. So if you have a spatial strategy, think about the different iterations that you can make from that one spatial strategy, and if you plot them together, all in a 3-dimensional space or even multi-dimensional space, something to visualize will be something like this. Yeah. So this is exploring the opportunities of the design space, and then testing it. So everything is red mean good, mean bad, and green means good. So what's good for, again? So optimization, rapid iterations, exploring the design space, evaluating your design, and comparing designs. Opportunities for design space. Design space are the full range of design variations based on your identified parameters. So this links back to spatial strategy. Octopus has a built-in design space visualization. You can also use Design Explorer. So Design Explorer is another plugin for Grasshopper. You can click on the link here. I'll share this presentation with you guys. But if I click here, this is something I did the other day. So if I copy this and paste it here, hopefully this works. So it's basically a tool for me to interrogate. So yeah, it works fine. So this was just me designing a box, right? A box, and the sliders have an X and Y and Z. Yeah, and then I can go here and actually select the different values of it. So the fitness criteria is based on the volume. So the higher the volume, I can actually limit them down. So these were the options I had for the volume here. Yeah, and it's just a tool where you have to export data in a specific way, and then you can just plug it in here. So you can see here, this is the actual data set that I created. So let's go here, paste it. And I've shared the script in the Grasshopper library. So if you look at the Colibri, I think I named it. So everything has a PNG, an image. So I exported things as images and as a JSON. JSON is just a file format. And then if I open this, you can see it's just a spreadsheet. So these are the different values. So X, Y, and Z. Volume, meter squared. Surface area, meter cubed. Surface area, meter squared. Total length of edges. So this is the one iteration. I have the image of the iteration and have the data associated with the iteration. Yeah. I just uploaded it to my Google Drive here. And if I copy this link, all that this does is if I go on get data, paste it here, and then load data, it'll actually access my Google Drive and load the data. So this is actually, the data is not saved within this program, it's just accessing it through here. Yeah. So Design Explorer is another way for you to explore these variations. You can see here all the different variations and these fitness criteria. So the area, volume, etc. Okay, so yeah, so I just want to take you through a tutorial with Galapagos. So we'll start with just a box. So if you just click on center box. Yep, just a center box. And this is just a simple box, right? So the center box, you can see the default values are 1, 1, 1, and it has a base in 0, 0, 0. So world XY, it's the same thing. Yeah? So that's the plane. And what I can do is just give it some sliders. So let's say 10, 10, 10. So now it's a 10 by 10 by 10 box here. Yeah? Maybe I want to give it more. I'll give it more with the in the Z, so make it go up to 20. If you double click on the slider, you can change the range. So I just want 20 here. Okay, so just like that. Okay, and let's say I want to move this. So I've covered these simple nodes before, right? So I'm taking the geometry, which is 10 by 10 by 20 here, and I'm moving it. The default value is 10 in the Z direction. I don't want to do that. What I want to do is just move it in the XY direction. So what I can do is unit vector, vector XYZ. And then I just give it a slider. So if I type in 0, if I type in minus 10 dot 10 should work. Yep. So that's just a shortcut for I need a slider from minus 10 to 10. Just give that in the X and give that in the Y. Display vector. So vector, and I just want to give it the XY plane here. So I'll just go over this again. I'm just turning off these just to avoid confusion. So here, covered what a vector is last time. So it's you can think of it as a force or as a magnitude of a direction, something that has a magnitude and a direction. So it has a direction of things. So you can see it's pointing towards something, and it has a magnitude. So the length of it is the magnitude. Yeah. And this you can see here. If you hover over motion, there's the arrow, and the arrow means it needs a vector type object. Yeah. And this is what I'm creating here, a vector type object. You can see that the vector has a 10 in the X and 10 in the Y, which means this is what I'm doing here, right? So I can change it to anything. Yeah. And this is just a vector doesn't really, it's not a real piece of geometry. It's just a force. So it doesn't really exist as a geometry. And what this does, this plugin here, just helps you visualize it so you can see it. Yeah? So you can see here, this is what a vector is, just 3 values in a list, similar to a points data structure. But here I'm just visualizing it, but it doesn't really exist in this location per se. Yeah. So here, by creating this vector, I can just plug it in here, and basically what I'm saying is take this geometry, which is the box, and move it by this vector that I've created. Yeah. So you can see here, I'm moving it. Yeah. So this is 10 in the X and 10 in the Y. If I go here, you can see it's moved 10 in the X and 10 in the Y, just because this is 10. So if I make this smaller, you can see, right? So I've moved it 10 in the X, this direction, 10 in the Y, this direction. I can also move it in the Z, but it's not important for now. Yeah, so I can move it here, or I can move it there. So let's say I have another one. This time I want another thing, but it's a bit shorter. So base. So now I've just copied and pasted this, right? I have two boxes. Let's just say I want 3, right? I'll just give this another. Another one, maybe let's go for 4. So I'm just creating different boxes here. Nothing to. So these are the 4 boxes, right? Box here. And this is me moving one of them. So I want to duplicate this for the other ones. So with this problem, maybe I'm trying to maximize or minimize their intersection, right? So make it, position them where there's, you know, they make up a bigger volume or a lesser volume if I want. So here again, I'm moving this, and I need to copy and paste this actually. So here, vector motion. Just want to move these down, move this here, copy these again. There. And give this a geometry and give this a geometry. So you can see now I've moved them all by the same magnitude, right? So they should all be, yeah, you can see they're all moved 10 in the Y and 10 in the X. And I can move these separately now, right? So here or here, I can move this one there. Let me get rid of these because they're just confused. Yeah. I mean, this is a basic example, but again, I want to show you the principles so you can take this forward and do something else with it. So here, now I need to come up with the fitness score, right? So the fitness score can be, I'll just use the solid difference. Not solid difference. I want union, sorry. Solid union. The solid union, I'm basically merging them all into one thing. So you can see here, there's, you know, they're all one geometry now. Look, even if I look at the output, I'm just getting one geometry, and I've given it 4 separate ones. You can see here they're not connected. Well, with the solid union, if you hover over, it just says performs a solid union on a set of reps, and this now is one object. And then I can calculate the volume. So fit the simple volume command, and I have the volume here. So panel, can get the outcome, and if I just move it here, so you can see. So you can see now, if I move things around, yeah, because I'm moving some of these objects, I'm getting, I need to click on this again. So if I move any of these objects, I'm getting a different volume. Yeah, because this, of course, when this moves inwards, there'll be a less of a volume. When it moves out, there'll be a bigger volume. You can see it. And now it's actually giving me 3 because they're disconnected. So it's calculating the volume of this, and volume of this. And that's not something I want. Yeah. So one of the ways I can deal with that is using just a list component. So list item. List item here. And basically what this does is just, I can search through a list. So if I bring this back, you can see that the outcome of this volume is a list of 3 objects because I have them separated here, so they can't perform a solid union. So it's calculating the volume for each of them. And with the list item, I can just give it a list and give it an index. So this is the index 0, 1, 2. If I want the very first item, which is index 0, I just give it an index 0, and then I get the item. Yeah. So here, this is the volume. Just do this. Well, that won't work. Okay, so let's use the sort. Not sort list. Is it map? What's the name of the component, Giuseppe? Do you know? If you remember, when you can sort a list based on different values, other values. Sort items.
Sort. Yeah, sort list.
Oh, yeah, it's sort list. It is sort list. Yeah. So, okay, so let me explain what's going on here. So I have the union. So 3 different volumes. Yeah. But here I only have the actual geometry. I don't have the volumes. Using this component, I can extract the volumes. Yeah. So you can see here the volumes: 2,560, 3,400, 9,552. Right. The problem with this list is it's not sorted. So the bigger volume is on the bottom, but I need to choose the bigger volume, maybe. Yeah. So with sort list, this is what I'm doing. So I'm giving it a list, and I'm giving it a values to sort with. And now if I go here, 3 values. Okay, maybe it's sorting it the other way. So I can go here, reverse. I can sort them ascending or descending. So this sorts them ascending, it appears. So if I go here, now I should always get the bigger value on the top. So 11,000, you can see there 9,000. What happens if I move this? 12,000. So you can see the bigger value is always on the top because I'm taking the geometries and I'm sorting them by their volume here. Yeah. And now I can. So the keys is sort values. Wait, no. Let's do this. I've messed this up slightly. So keys, result, values, keys. There we are. Okay. Reverse. Okay, so this should work now. So here, and now I can actually choose the bigger volume here. So you see here, there are actually 2 volumes, but based on sorting it here, I'm sorting the volumes based on their volumes, so the bigger one, and then I'm selecting the bigger one. Yeah. So if I move this around, you can see at some point, some of them will. You can see this has become 1 volume now, but once I move it here, become 2. So it's selecting the bigger one. Same here. So if I move this and it goes out, it's just going to select the bigger one. Yeah. Okay. So. So this is what I'm going to use for my fitness evaluation, right? So I'm just taking the volume and using this one here. So the keys. I only need the volume for the fitness evaluation. So if you need the Galapagos plugin, you just type in Galapagos. If you go on Food for Rhino, so Food for Rhino is where you would find most of your plugins over here. So Food for Rhino. And if you go on Grasshopper apps, maybe you want to sort by downloads, so you'll find the more popular ones, and you can see these are by far the most popular ones. So Ladybug Tools, we did a tutorial on. Kangaroo, so if you want to do circle packing and stuff like that. Physics Engine, this is a plugin you might want to have a look at as well. It's useful for generative spatial strategies and other stuff here. You can have a look at. Yeah. 3/4 of coding is always Googling, right, Giuseppe? Sometimes you just have to Google more. Do your study. As Enrique said, knowledge-based. Sometimes you won't find the solution, but if you look for something like I don't know, how to split box Grasshopper, you'll find the Grasshopper forum. Someone's already asked the question and someone's already kind of given them the answer, right? So there needs a lot of kind of researching, just trying to figure out the problem. Okay. So back to this. So let's say I want to maximize the volume that I have, right? And this, like, you have to choose what your fitness criteria is, right? So some of you might be working with light as something you want to prioritize. Some of you might want to think about reducing routes. So this can be a fitness criteria. Yeah. The overall number of kind of circulation routes, for example. Some of you might want to look at so many things, exposure to sunlight, the size of windows, all these can be translated into fitness criteria. So the genome, I want to connect the genome to these sliders. So again, with Grasshopper usually works left to right, but with Galapagos it's the opposite way. So you just have to connect them, hold down Control to connect multiple ones. Sorry, not Control, hold down Shift. And just connect these, right? And I'll show you how Grasshopper actually changes the sliders for you to look at. Here, here, here. So these are the sliders I'm telling it to change around. Yep, and this here is the fitness criteria. So other way around again. Okay, so let's see. I just want to copy this, so I'm selecting the geometry. I want to see which geometry is outputting, and I want to hide all these. So preview off. Preview off. Okay, so again, similar to what we did earlier, you just double click. So Galapagos is always good to use with a different plugin. So I showed you earlier how to use it with Weaverbird, not Weaverbird, sorry, Ladybug tools. So environmental optimization, we usually use Ladybug tools, yeah. So anything for environmental optimization. So again, okay, so I go here. I want to maximize the volume. So I keep these settings as maximize. I go to solver, evolutionary solver, and then start solver. And you can see it's going through all the sliders. And if I move here, you can see what it's actually doing, right? So it's a tool to crunch numbers. It's not something that I'll generate. I came up with the basic logic, the strategy, if you like, and then what it does, it just looks at the different numbers. And as you can see with time, it's converging, yeah? So it's not as sporadic as it used to be at the beginning. That's because it's looking at the solutions and which ones are going in the right direction, and it's just continuing in that direction. So it's, rather than start all over again and change everything from the beginning, it's just trying to refine, if you like. And as you can see here, they're more controlled, right? They're not all over the place. Yeah. And then you can actually look. So these are all the populations. So the population, each one of these points, I believe is 100. No, it's not 100. But these points are different iterations, and it's just going. And you can see it's improving. So at the beginning, it was stagnating, but actually now it's finding better solutions. That's why it's going up here. You can see there. And this small plus sign means it found a better solution. Yeah. So again, this is like I can actually select some of the, so you see here, because I've given it 8 sliders, each one of these vertical axes shows me as a slider. So this iteration that I just clicked on, sorry, just click here, for example, shows me this is one of your iterations. So the slider for A is here, B for here, and this is the value, right? So if this is 0 to 1, slider A would have been something like 0.6. You can see here it reached a very good point, and now it's trying something else. Yeah, to see if there's any better value. Yeah. So I'm hoping this simple example makes a lot more sense. Have you been able to make it work? Has anyone not figured out anything?
I have a question about that middle graph that you just indicated to, that was showing slider information.
This one?
Yeah. Is that almost like a histogram? I don't know how to perceive it. I don't know how to read it at all.
No, this is just showing you the parameters. So you see here, these are the different iterations, right? So if I click on this reinstate, I need to stop it first. So click on this. This apparently is the best one for maximizing volume. So I click on reinstate, and you can see they're barely touching each other.
Yeah.
Right. To maximize the volume, and if I move down, you can see this is changing as well, right?
Yeah.
And this is what was telling me. Look at these: 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 inputs. You can see the first one is -6. I don't know which one's which, but this point here is basically a -6, and this one will be a 3. So if this is a, think of this as a z-axis in a typical graph.
Yeah, that's where I'm struggling. Okay.
Yeah. So this will be the maximum value, which will be a 10.
Yeah.
This will be a minimum value, which is -10. All these sliders go from -10 to 10.
Yeah.
10. This will be -10, and it's just showing me the parameters that I've chosen, right?
And then you mentioned earlier that as it progresses, it learns and it becomes more accurate in the iterations. Does that mean generally that the last iteration will, in theory, be like the best one, or the last couple?
Generally, yes. Generally, yes.
Okay.
Of course,
Okay.
there's always exception, but that's the point of using this, is to come up with these, right?
Okay.
So hopefully now you know how to read this, right? So you can see
a little bit better. It's very similar to like a photographic histogram, which is where I'm being confused, because I spent so much time looking at those that I'm kind of like overlaying them, and it's going to take a bit of time to break that, I think. But
I mean, you know what's going on here completely now, right? What's not clear?
No, I get it. So every point where there is like a defined point, its vertical position indicates its position on the slider. So the higher up, the closer to 10. The lower down, the closer to -10, right?
Yeah, and you can see the best ones here. The best ones here are all very similar.
Yeah.
I go down.
And is it showing on the back there with all the wireframes? Those are prior iterations.
Those are prior. So I can select on one of these, any random one of these, and go down and find it, whatever it is.
Okay.
But because it knew that this area is kind of where the better outputs are, it keeps on iterating more in these areas. That's why it's darker. Yeah. And this here is just showing you the value. So green is a high value.
Yeah.
So you can see here high. You can see here just before the end, it's very high, and that's what this shows. So these are not. I'm just trying to explain to you how to interpret them.
Yeah, well, that's what I was struggling with, because up till that point, I didn't know how important that middle graph would be, and I can kind of see it's like, I can kind of see the use of it now, but I was just not grasping that at all.
Yeah, so you can see here, this is the second half of the process, and almost exclusively it's just looking at this kind of. You can see the blue area, right? And this is the where it converges. So it's exploring this area more. Well, at the beginning, it was exploring everything.
Yeah.
And that's pretty fine.
Okay, sweet. Thank you very much.
Yeah.
I mean, the thinking behind this, you have to imagine it is like it's simulating a little bit Darwin evolution. That's what it's doing. That's why it's called genetic algorithm.
Yep.
So you have a population of options, and then is coding each one of them, and then is getting the best one and mating them. So it's taking a little bit of slider numbers from one and a little bit of slider from another one.
Selective breeding, basically.
Exactly. Yeah? And when you see, so the top part of that graph, you see that there are numbers from 0 to 39. Each one of those is one population.
One population sample. Yeah. So this is not 39 iterations, it's 3.
It's representative of a group.
And when you get, if you go back 1 second, I'll show you another. You know what, at that point, at the 18th generation, when it grows again, the population, it's because it has introduced a mutation to the population. So it's put a random value, and that's why it's growing again.
Okay. And can I ask one more question? Why does that top graph, why is it separated into a dark orange and a lighter yellow? The area, almost the area between the line.
So think about this as the population, or the range of the population here, right? So the red will show you the kind of trend line, whereas this one here you can see is converging, and then here is struggling to find a better solution. Now we keep on saying it struggling.
So it searches a wider range.
Exactly. So exactly what Giuseppe said. So here is like, okay, I've reached the best I can with this population. Let me go a bit random again and expand and see whether I can get somewhere else. And you can see where there's a positive, this plus here, it means it's found a better solution wherever there is this plus.
So if you ran this, like hypothetically, if you ran this infinitely, would you see that trend of it narrowing and widening continuously?
Yeah, until it exhausts every single possibility. But the actual possibilities that I have here with 20
Yeah.
variations per slide, we're going into, it's 20 up to the power of
How many sliders
8.
you have?
I think
Yeah.
20 to the power 8, so it's a massive number, right? So
Yeah, of course. But the reason I ask that is because then when you say with each iteration it gets better and that the final iterations will be the best,
yeah.
does that mean that there's so you wouldn't find much value in taking those early iterations, right? There wouldn't be much value because those iterations are so random, yeah?
So if I let's take this and this is the worst one. Let's reinstate.
Yeah.
So this is where they all mush into each other, right?
Yeah, they're all conjecture. Yeah. But the reason I asked this question though is because you have what was the number? 20 to the power of 8, was it?
I think that's how you calculate.
Yeah.
I might have got it wrong, but
No,
Yeah,
that's fine. That's fine. The reason I ask is because that's such a large number. If you don't exhaust those options, like in the grand scheme, aren't we so early in that timeline? Aren't we still very, very early in that timeline?
No. It's because it does it in a. That's the whole point, right? It's with the population sample. Now,
Yeah, you're using.
These will all be very similar, so it already knows that there's no point. There's no point for it to explore here further because they're so close to each other.
Yeah.
So it'll actually expand on these better ones.
Mm-hmm.
Now these can go on for a long time. Then you reach a point where it's not improving, and if it's improving, it's negligible.
Yeah. So would we expect if you were to continue this now, because if again I might be misunderstanding, but if we're so early in the timeline, wouldn't the last part in this graph, wouldn't we be expecting it to widen again?
Yes. Yeah.
Well,
Okay.
I mean, the tendency is that it goes narrowing all the time, but every now and then it can introduce a mutation, so it can grow bigger. But then, like, the overall tendency is to go narrower and narrower. So you expect that the last generation has the best result.
Yeah.
But to make this this code work, they added basically a degree of randomness. And this degree of randomness means that you could have possibly the best solution in the first generation.
Yeah.
But like as a tendency, it's always going to a better improvement, basically.
Okay. But is it almost like it's somewhat futile unless you reach that last generation and know all of the potential possibilities, or am I?
No.
Okay.
Because well, it depends. But let's say here, I'm not really helping it because I'm giving it quite a big range.
Yes, so many possibilities.
Exactly. I'm giving it quite a big range, and at least I'm not giving it 10.001 kind of 0.01 steps to look at.
The reason I ask this is so I'm deciding whether or not to like treat this almost like a render where you leave it running overnight, or if it's something that you leave for an hour. I don't know.
Overnight. I think it'll reach a point where I won't be able to find any more. It'll reach a point where things might be negligible.
Yeah. Okay.
It'll improve by a very minute.
So I'm just gonna have to learn that by getting a feel for how many variables are included, and to what the range of each variable is, and then eventually I'll get the feel for when it starts to become negligible, right?
Exactly. Yeah.
Okay.
Yeah, exactly. I mean, usually.
Go on.
No, what I'm saying is that usually, basically, there are two ways that you use to decide when the algorithm is working or not. One is just saying stop after the 1000th generation.
Yeah.
Or you can set up some threshold and you say, okay, if my volume is bigger than X meter cubes, then I'm happy enough to stop the algorithm. That's how you could approach it.
Okay. Yeah. Sorry if that took up a bunch of time. I didn't want to.
That's exactly what we need, Karim, man.
Oh, there we go. Hey, you're welcome. I'm sorry.
I think everyone else is benefiting from the question. So, yeah, no question is a wrong or stupid question. So, good on you. So hopefully you get the idea, and through this kind of more practical example or a simpler example, it makes a bit more sense. Yeah. So you see, it always start converges and then it goes out. So